Hey guys, we're going to go ahead and take a look at how you can solve quadratic equations by finding square roots. So just to kind of start and understand what we're looking at, we'll be looking at solving equations that have a squared variable. So if you were to think about what your solutions would be to x squared equals 4, you know that the opposite operation of squaring is taking the square root, so then most people would say this answer is 2. But it's actually both positive and negative 2, since if we work backwards and plug those both in and square it, we know that positive 2 squared is 4, but then also negative 2 times itself, negative 2 is also positive 4. So every time you take the square root of a number, you're going to get two solutions, both the positive and negative version. Just some terminology to keep in mind. A radical is just any kind of root bar, and the number on the inside is the radicand, and then the radical sign would be your root bar. That could be a square root, which you see here, or a cubed root, or a fourth root, and so forth. Okay, so a couple properties to keep in mind as we're looking at doing radical stuff. Product property would be anytime you have a number inside a square root bar being multiplied together, you can basically break it apart into two other values. The quotient property states that if you are dividing two different numbers or you have a fraction in a radical bar, you're allowed to separate that fraction and just put your radical with the numerator and the denominator. So a couple of examples to kind of refresh in your brain. If you have the square root of 40, we can break that into any factors of 40, which would be 4 and 10, and this is what we looked at last class. And then you're allowed to take the square root of 4, which is 2. 10 does not have any perfect square factors, so then you're done. If you have something like the square root of 3/4, for right now, we can actually separate that into square root of 3 over the square root of 4, and then because the square root of 4 is a perfect square in the denominator, that gives you 2. Here's a couple other examples of simplifying radicals if you want to try them, and then you could press play to check them. But if you have the square root of 500, we're looking for the biggest perfect square factor, which is 105. That means we can separate those if you want. I know some people skip that step, but some people prefer it because it makes it easier to see that when you take the square root of 100, it's 10. 5 you can't, so it stays in. Second one, you have 3 times square root of 12 times square root of 6. So if you have one like this, you're going to multiply the two square roots together first and combine those, and that's going to end up giving you 72. Now if we look at 72, we're looking for the biggest perfect square factor, which would be 36 and 2. Again, you're looking to take the square root of 36, which is going to be 6, and then last is to multiply the two numbers on the outside, which would be 18 times the square root of 2. And then the last one, the square root of 25 over 9, since these are both perfect squares, you can actually just square root each and get 5 over 3. Now, technically, all of these would have both the positive and negative answers for them, but when we're just simplifying radicals, you're not going to see the plus minus with them. When we're using radicals to solve equations, that's when we're going to add in that positive and negative with each of our answers. Okay, so something you're going to see that's probably new to you guys this year is when we need to rationalize a denominator, and that basically means that you cannot have a radical in the denominator. And the word rational is just like in the subsets. Rational numbers are decimals that stop or repeat. What's not considered rational are square roots of numbers that are not perfect squares. So if you happen to have a non-perfect square as a denominator, you have to get rid of it. And there's a little saying that can kind of help let you kind of visualize it. No tents in the basement, almost because a radical sign looks like it could be a tent. So this would not be okay to keep there. You would have to rationalize it. By rationalizing, all we have to do is make that not a non-perfect square number. And the easiest way to do that is whatever that radical is, you're just going to multiply by that same radical. And the reason that we're able to do that is if you look at this, the square root of 3 over the square root of 3 is the same thing as 1. So it's like using identity property, and you're allowed to make 1 anything you need. And by doing that, the square root of 3 times the square root of 3 would be the square root of 9, and then you could take that square root, and now you no longer have that irrational number as a denominator. So here's a couple of other examples. So we have the square root of 25 thirds. Again, you could separate those two apart. These are ones where it probably makes more sense to do that. And then what you're going to do is we're going to rationalize that denominator. I know my numerator is actually just 5. For right now, I'll kind of just hang on to that. But I'm going to get rid of the square root of 3 by multiplying by 1. But for us, that's going to be whatever your radical on the bottom was. So now this is going to make the square root of 25 on top times the square root of 3. I'm going to keep them separate again. I know this is really just 5 over the square root of 3 times the square root of 3, which is really the square root of 9. And you normally would put the two numbers on the numerator together, but I'm keeping them separate because the square root of 25 is 5. So my final answer here would be 5 times the square root of 3 over 3, and I'm good now because I no longer have that radical on the bottom. Next one, the square root of 211, so you would separate to 2 and 11, and again, I'm going to get rid of the square root of 11 by rationalizing, and that's just multiplying by 1, or whatever your denominator's radical is. So the top becomes 2 times 11, which I am going to put together for this one, which is 22. The bottom is going to be the square root of 121, and we know that that's just going to end up being an 11. Now the numerator, if you had a way to simplify more, if there was a perfect square factor of 22, we would do that, but there are none, so we're actually good at this point. Go ahead and practice rationalizing these denominators just to see how you do, and then press play when you're ready to check. Okay, so example 1 should have been the square root of 70 over 7, and that cannot be simplified anymore. Number 2, what you needed to do is first multiply by the square root of 5 over the square root of 5, and that square root of 40 for your numerator has a perfect square factor of 4, so then you would simplify the numerator one more time, and you end up getting 2 times the square root of 10 for your numerator over 5. Number 3, so when you have a variable as well, you cannot keep that radical on the bottom. So we're going to go ahead and multiply by the square root of 3x on top and bottom. That's going to give you 96x on top and then 9x squared on the bottom. You take the square root of 9x squared, you get 3x. The numerator can also be simplified since a perfect square factor of 96 is 16 and 6. So then we take the square root of 16, it comes out as 4. You're left over with 4 times the square root of 6x over 3x. And number 4, final answer was square root of 2 over 3. This had a lot to simplify. You could have also simplified this a little different than the way I did. Technically, at the very beginning, that denominator 9, you could have just taken that as the square root of 9 and had 3 on the bottom, but you would have still had that radical with a y left over. So if you did it that way, you should still be able to get to the same answer, but I just went and multiplied by the square root of 9y over the square root of 9y, and got 18y squared, which could have been simplified to 9y squared and 2, which you see right down here on the bottom. And then that gives you 3y times the square root of 2. Denominator's 9y, and then this 3y and 9y on the outside can be reduced, if you think of it as a fraction, and that ends up being 1y, or just 1 over 3, or 1 times the square root of 2 over 3. So now we're going to go ahead and look at applying these to equations. So these are still equations. The ultimate goal is to get x by itself. It's just going to have a square root bar somewhere within as you solve. So if you think of solving equations, you work backwards. So in number 1 here, we would go ahead and subtract 3 from both sides. And then we would have a negative 5x squared equals negative 12. Then we would divide by that negative 5. And I know a negative divided by negative is a positive, so now I have x squared equals 12/5. My last step to solve for x is to go ahead and take the square root of both sides, and this is going to be where we get that positive and negative solution of the square root of 12 and the square over the square root of 5. So because of what we just looked at, you can't keep this, so we're going to go ahead and rationalize and get rid of that square root of 5 over the square root of 5, and that's going to end up giving us the square root of 60 over 5. And then we're looking for any any perfect square factors of 60, which I know I do have 4 and 15. So if I was to simplify one more time and take the square root of 4, I'm going to end up with 2 times the square root of 15 over 5. And because, again, this is an equation, we want to show all solutions, so it's both the positive and negative version. So this should be your final answer. Okay, the second one over here is kind of a little weird. Again, if we're going to work backwards, we have to keep the parentheses there. We're going to go ahead and get rid of the 3 first. So we're going to divide both sides by 3. That leaves us with x minus 2 quantity squared equals 7. And now I can't necessarily get rid of that negative 2 on the parentheses because of this outer exponent here. So I'm going to go ahead and square root to get rid of that right now, which is going to leave me with x minus 2 equals positive and negative the square root of 7. And now I can go ahead and get rid of that minus 2 by adding 2. So this one's just going to kind of look weird. You're going to end up typically seeing this as 2 plus or minus the square root of 7. You normally will always put your constant before your radical bar, and that would remain your final answer. You can't simplify the square root of 7, and you don't have to rationalize here. Okay, a couple of other examples. You're going to go ahead and add 6 to both sides here. You'll have 4x squared equals 48. Divide by 4. We have x squared equals this. X squared equals 12. We square root 12, And again, it's going to be both the positive and negative version of the square root of 12, but 12 has a perfect square factor of 4. So if we simplify that down one more time, we're going to get the positive and negative version of 2 times the square root of 3. Fourth example, we've got to save those parentheses for last, so we've got to get rid of that 1/5 by multiplying by a reciprocal. Now we've got x minus 4 quantity squared equals 30. I'm going to go ahead and square root both of these sides to get rid of that, and then I would be left with x minus 4 equals the positive and negative square root of 30. Looking for any perfect square factors of 30, and there are none, so we can keep that, and then we're going to go ahead and just add 4. So again, your constant will come out in the front. It's a positive 4 plus or minus the square root of 30. And that would be your final answers. Here's a few for you guys to try on your own, and then press play when you're ready to check. Okay, so example 1 should have ended up being plus or minus the square root of 7. The second one would have ended up being plus or minus 2. The third one, plus or minus 3/2. And the fourth one, plus or minus 3 times the square root of 10 over 2. So hopefully you did well on those. If not, you can check through the steps and see if you made any mistakes and fix them. And that is it for this. We will practice more in class, and then we get to look at my favorite, which is I. See you guys soon.